So thanks, Jerry, for actually hosting this series, but also for asking me to give a talk. I think I need an introduction. My name is Matt Newville. I'm a beamline scientist at the University of Chicago, running a microprobe beamline at the APS. And I'm going to tell you about that beamline. We do a lot of X-ray absorption work at that beamline, but not exclusively. And so even though this is an X-ray absorption and related techniques journal club, there'll be some other things in this talk. Again, so my co-authors on this are my partners, Tony Lanzarotti, Steve Sutton, Peter Reng, and Mark Rivers, all at the University of Chicago. We've all been there for many years. This is what happens when beamline scientists get old and work by working together for a long time. So GSECARS is one of the 35 sectors at the APS. The Center for Advanced Radiation Sources at the University of Chicago actually operates 3 sectors we're closely associated with each other. GeoSoilEnviroCARS, or GSECARS, runs 2 separate beamlines, two undulator beamlines and 2 bending magnet beamlines at the APS. That's one sector. We run as a national user facility ourselves, so that 85% or more of the beam time of the 200 days a year beam time are given through the general user program to outside users. We collaborate with many of the users, so and many of them have given talks already in this session. And most of the work that we do at GSECARS is earth science work. The funding is from NSF, some from DOE, and some from NASA. GSECARS is a fairly well-endowed sector at the APS. We have 11 scientific staff, 4 support staff, and 5 postdocs. And our publication record is pretty good for the APS or any other facility. And that's basically the appropriate level of staffing and funding for any one sector. Most of them are woefully underfunded, and we're close to what should be funded. Again, we have 2 undulator beamlines and 2 bending magnet beamlines that all run simultaneously. For the downstream undulator is mostly used for either diamond anvil work or large volume press, high pressure research. There's also a general purpose diffractometer that does some surface and interface diffraction, some high pressure work, some inelastic scattering, and a bunch of other random methods. On the upstream undulator, it's dedicated to the X-ray microprobe that I'm going to tell you about today. That's X-ray fluorescence, X-ray diffraction mapping, and XANES and other spectroscopies. On the bending magnet, we have 2 beamlines. One that focuses on that has the straight white and monochromatic beam that does diamond anvil cell, large volume press, and X-ray computed tomography. We used to do bulk XAFS on that beamline, but we stopped doing that several years ago. And then we have a side branch with a side deflection that does diamond anvil cell work and surface diffraction at fixed wavelength. The way we got to 2 undulators is part of the history of this beamline, and so and impacts the microprobe. So I'm going to tell you a little bit about this, even though it's old news at this point. Around 2010 to 2012, the APS and our funding agents encouraged us to take our one sector and make it into 2 undulator beamlines. So we canted the undulators, which is to put 2 undulators in the straight section of the storage ring with a 1 milliradian bend between them. 1 milliradian isn't very much, and even at 50 meters from the source, that only gives you a separation of the beams by 50 millimeters. So you have to use mirrors to separate the branches well enough to use them. Of course, X-ray mirrors are also low-pass filters. So one of those branches will be relatively low energy. And at the APS, and for high pressure work, being able to use 50 to 100 keV X-rays is very important. So we decided to take that as an opportunity and say that the branch that is kicked out by mirrors will be a microprobe that is dedicated to relatively low energies for the APS, that is 30 keV and below. We also, with that caveat, or with that constraint, we also asked and got for a dedicated undulator that could go to sulfur K-edge. So the APS provided us with a 3.6 centimeter device, which will allow us to do sulfur and chlorine K-edges. That's a unique undulator at the APS, not the only one that can go to low energy, but the only one with that energy range and that size. And when I get to the APS upgrade, I'll talk about how that's going to work too. Right, okay. So the optics for the X-ray optics for the microprobe then are fairly unique and may not be what you would have thought you would have chosen. We have with the beam coming from right to left in the front end, we have slits for the white beam before the monochromators. The monochromator nested, so the inboard mono, the outboard mono. Then we have the mirror system after the monochromator, and then beam viewers, which are very important. I won't go into much of the details of that. Very important for the stability of the beam. And then at 40 meters from the source, 42 meters from the source, we make a secondary source. We have an aperture to make to focus to a secondary source, so that in the vertical, we focus the full undulator beam, and in the horizontal, currently, with the current APS, we make a secondary source and refocus that, so that at the end station, with small KB mirrors of the normal sort, nothing too fancy, they're good, but they're nothing too fancy, we get a final focus of about a micron in each direction. So in the end station, now 50 meters downstream, the beam comes in. Here's the branch for that flies by for all the other techniques downstream. We have the beam coming in here, some slits, some filters that we can put in the beam to attenuate or make a shutter. And in an ion chamber, X-ray focusing mirrors, KB mirrors that have two stripes, both silicon and rhodium. And then the sample will sit on a stage here, and then we use almost always an energy dispersive X-ray fluorescence detector to do the fluorescence analysis. So we have a good optical microscope also. I should say that this whole path from here, this entrance bench with the slits, the ion chamber, and the focusing mirrors are all in helium, so that we can easily get to the sulfur K edge. Actually, there's a window, there's a beryllium window and then a kapton window. And that kapton window there, to prevent the helium, prevent the air from attacking the beryllium, actually does a fair amount of absorption. And so that's why our flux at sulfur is actually down to the mid-10s instead of the 11s or 12s. So with the sample in air, we get fluxes in the mid-10s to the 13 level that in a micron or 2 spot size. We can easily switch the energies between 2.4 and 27 keV, and most of the work is done in ambient conditions. We do have some capabilities for doing either high pressure work with diamond apple cells or low temperature. We're working on making that better. Most of the work we do is actually ambient, and that's mostly X-ray fluorescence mapping, some X-ray diffraction, a lot of XAFS and XANES, and a little bit of HERFD and RIXS, and I'll talk about those as we go. So a very important consideration for an X-ray microprobe or any beamline that does XAFS is the monochromator. The monochromator that we installed in 2012 was, at the time at least, a great improvement in what we had, and I think an improvement in what most other people had at the time. I think these are now more common. So this monochromator uses an air bearing with a ferrofluid seal and a very high direct drive, high torque motor. There's an on-axis encoder that is actually correct and accurate, that measures the angle to 133 nanoradians. We have both silicon 111 and 311 crystal sets. The cooling is indirect liquid nitrogen, and we know that we can improve the cooling. It's good, but because of the imperfect cooling, we actually use those front end slits to reduce the power load on the monochromator's crystals, so that they don't so that they stay in their nice non-bent form. The motion control system that we use allows rapid scanning. So we do continuous XAFS almost exclusively now. The limitation for that, for how fast we can do XAFS with this monochromator, is actually not the monochromator, it's the undulator. We have to scan the undulator with the undulator gap. That's a 2 meter device that we want to control to micron precision, and we can do that at about half a second per EV step. So that's as fast as we can do XAFS, and we're hoping that gets improved in the upgrade. For the monochromator, one of the most important concerns for us was energy stability and reproducibility over time. So an early test we did was just to see how reproducible and how static that beam was. So here are iron K-edge pre-edge peaks, the kind of thing that we measure all the time. This is data that was taken over 2 days where we would go back to the same sample that we know does not beam damage. So this is the same stable dry sample using the silicon 311 crystal. We repeated 34 spectra over 46 days. As a bonus, this was in top-up mode, in non-top-up mode. So there was a varying heat load, so we can study the heat load. And we're going to measure how much those pre-edge peaks shift over the couple of days. Here are some sort of energy and angular values to put together. So the core level is about a volt, the Darwin width is about 0.2 of a volt, and the encoder step is a milli-electron volt at these energies. So repeating that and measuring the centroid of those two peaks, what common analysis approach, we see that the centroid varies by something like 0.01 EV, maybe a little bit more than that, with a typical width of or uncertainty in that centroid of 0.02. So basically the energy does not drift at the level of detection. Also, the energy steps that we took during these scans were 0.1 EV. So you can see those are 0.1 EV steps. The centroid moves by 10 times or 8 times smaller than that. One question though is there an effect of heat load? So here is the centroid that we find is a function of the ring current, which was changing. And you can see that there's effectively no heat load dependence on the energy. So we know that the energy is stable, and that actually greatly improves our ability to do XANES analysis where we can measure the standards once or occasionally and know that the energies are reliable and not drifting in time. The other important feature or piece of equipment for an X-ray microprobe beamline is the fluorescence detector. So we're doing energy dispersive fluorescence detection basically full time. You know, really, this detector is on 200 days a year, so we really needed to work reliably and well. So currently, we're using silicon drift detectors. We in March of this year, we received the Canberra Mirion SXD7, a 7-element detector, and we're using those with the quantum express 3 electronics. The detector uses a cryogen-free cooling system to get the detector head to -80. The detector elements to -80 degrees C, and then with that and these new-ish, relatively new CMOS preamplifiers, we can really get to count rates that are above 4 megahertz. The top of the dead time curves range from 4.5 to 5 megahertz per channel, and the energy full width half max are actually very good. So the sort of the Fano limit, the best you could ever be able to do with silicon is around 120 EV. We really see 125 to 100 or better than 130 at the lowest count rates, and it goes up, but not very dramatically. And the spectra are clean and analyzable even to 3 megahertz, and dead time corrections work well to 2.5 megahertz. And that allows plenty of room for sort of headroom in an amplifier, so that in fluorescence maps, it's okay to saturate briefly during a map, and it won't destroy the signals. For XAFS, we can go up to 1 megahertz or so really well, and if the white line goes up a little bit above that to maybe even 2 megahertz, it's acceptable. For sure, the workhorse method of the X-ray microprobe is scanning. So these are scanning probes, and so X-ray fluorescence mapping needs to happen, and we need to do that every day on basically every sample. So being able to collect X-ray fluorescence maps that is very important. We scan the sample continuously back and forth in what is that, a snake or an S pattern in the X-ray beam, triggering the detectors, the fluorescence and any other detector at fixed intervals, usually 5 to 50 milliseconds. So now the 7 X-ray fluorescence spectra are then streamed to HDF5 files and then merged, and we take the ion chamber and the position data measurements as well and merge that into a final data set. We're normally using simple regions of interest, so just the areas under these curves as the initial maps for elemental distributions. We can, with some effort and with some amount of precision and accuracy, account for peak overlaps and known efficiencies so that we can make better elemental abundance maps in post-processing. This is something we don't do. I would say we don't do it often. We don't do it regularly enough to really know that we're doing that perfectly well. Most of the people we work with just want to find stuff, and so quantifying the quantities, quantifying the values of the abundances to within factors of 2 is not usually our main emphasis, but we can do it. So then we make X-ray fluorescence maps that might look like this. This is 2 leaves of brassica that are known to be hyperaccumulating plants, one grown in isolation and one co-cropped with a legume. This is a 10 by 9 millimeter image of 2 leaves. Like really, we stuck 2 leaves on double-sided tape. This is a 16-hour map at 15 milliseconds per pixel. And this shows the distributions of manganese in the trichomes and the roots or the hairs on the leaves, and that the zinc and potassium and calcium distributions are very different for the co-cropped and isolated growth plants. This data is actually with a high school group from Karen Beardsley and Glenbard East High School in Lombard, Illinois. And I think that's a really good place to stop for questions and ask, so that's sort of how the microprobe works. And are there any questions about what I've said so far?
There are a few questions. Cheng Jun, would you like to start?
Yes. Matt, I have a quick question. So you mentioned about the horizontal source, secondary horizontal source. But after IPS upgrade, do you still need a secondary source?
Yeah, we expect that we don't need the secondary source after the upgrade. The beam size after the upgrade will be round-ish. It won't be perfectly round. So we believe we won't need to do that. We do have to, however, and I'll talk about this a little bit more, but we do have to replace those big mirrors because they're not flat enough to preserve the image, the source size in the horizontal. So we need to replace those mirrors.
Oh, okay.
We spec them for the current APS.
Okay. I hope
right,
for another. Yeah.
Mm-hmm.
Okay.
Go ahead.
Yeah, I have another question. Yeah, how normally how long it takes for you guys to switch between the 111 and the 311?
Yeah. Okay. So that's a script that we run, and it takes a couple of minutes.
Okay.
It takes a couple. It takes a couple of minutes. It takes about a minute for us to switch, basically, like doing large energy moves, going from, iron to arsenic takes a couple of minutes, and that's mostly waiting for the mirrors to move, the big mirrors to move if they have to change stripes.
Okay.
And changing crystals is a couple of minutes, and we normally dial in the offset value, and it works well, but we will typically rerun a foil when we change energies.
Okay.
Yeah.
All right. Thank you.
Or change crystals. Yeah.
Very impressive. So quick.
It's just some motors, right? So they just move it and they work. So actually, I should say that I hinted at that beamline diagnostic is really important. So let me answer the question the long way. In order as we change energies, we have big angular motions, and if there's a little bit of a roll in that monochromator, it's really bad for us because we bounce horizontally twice. That will amplify any roll, and then we have to get the beam through small slits. So at the beginning of the run, we spend a little bit of time. We know where these values are, and they're reproducible, so we don't have to spend an enormous amount of time making sure that as we rock the crystal, that the beam points to the same place to very high accuracy, and then driving is very easy. But we have to have that work. For the bounced and secondary source, because we keep that secondary source we keep to be in the range of 25 microns.
All right.
Yeah. Okay. Sorry, the answer was so long.
A good answer. You should continue, Matt. Thanks for the break.
Yeah. Okay. So now I'll talk about a little bit of application, a little bit of variation on the themes of doing X-ray fluorescence maps. And one is that we can do X-ray fluorescence tomography. Really, this is just mapping. It's just that we map in X and theta. So we spin the sample as well as instead of rastering back and forth. But it's the same. Actually, it's the same process, and then it's just math to turn it into the data sets we want. So here's a map where we spin the sample at 360 degrees in half-degree steps and across a 400 micron seed. This is a Arabidopsis seed, one of the well-known controlled plants for genetics. And this is then the virtual slice through that seed. That's the same data set. That's just math to turn that into the seed. And you can see in this view then the radicle, the embryonic root, and the cotyledons, the leaves. Actually, you can see that here in the manganese in green, that's the manganese that's needed for photosystem 2 that would be inhibited by Roundup. And that's on the outside of the leaf. As those two leaves pop up germinate out of the root, that's where you need to do the photosynthesis. So we could do 3D volumes. In fact, we do 3D volumes for this, but these are scanning probes. So that took about a half an hour, that slice, an hour and a half, sorry. And we sometimes do 3 dimensions. What these people were interested in, so this is Tracy Punchon and Andreas Events from Dartmouth, they were interested in looking at the genomic structure. So they wanted to knock out some of the genes and see how that affected the metal uptake. They knew what this would look like, but they want to get the quantifications for where and how much of the manganese and iron is redistributed with genetics. So in some ways, genome for them was the third dimension of interest. But for some samples, we really do 3-dimension sets, and 3-dimensional spatial 3 dimensions data sets. So let's see if I can advance past that. Okay. Yeah, so the X-ray microprobe is inherently multimodal. We're doing X-ray fluorescence, X-ray absorption, X-ray diffraction. We switch between them continuously. In fact, sort of the normal work mode is to make a map. This is a map that I made earlier this week on something that was purported to be a glass. It wasn't quite perfectly glassy, so we'll make a X-ray fluorescence map in order to be able to decide where to do the analyses. So in fact, I think I will say that actually some of the talks that were given earlier in the session from Megan and from Mary Jo Browns and from Darby Dyer would do the same thing. They would show maps, and then we did the XANES analysis here, here, and here. And this is our typical mode. So here are 3 XF scans and done on a map to isolate mineral grains or inclusions or find glassy areas. We can also do redox mapping. This is something we get asked about a lot. So here are some redox maps. I won't go into too much detail of the science from David Fike and Catherine Rose at Washington University. This is basically trying to figure out some climate change analysis from 450 million years ago, how the climate changed then. And so they were confused about there was confusion about the sulfur oxidation and concentrations in some bryozoan fossils. So doing redox maps at the sulfur K edge, basically making a map of sulfide and a map of sulfate, we can see that the sulfides were very highly localized and not in the fossil. The fossil was all sulfate, and there were these detrital sulfide grains on top. So we do a lot of sulfur X-ray, sulfur XANES, as well as sulfur mapping. And redox maps can be done at many edges. We often find that doing a map and then XANES is a little bit more efficient than doing redox maps, but we do both. We also do some combined X-ray fluorescence and X-ray diffraction mapping, where we measure the diffraction map at each point in an X-ray fluorescent map. We measure them simultaneously. So here we have a Eiger 500K detector that I'll come back to in a bit. And the sample stage, this is one variation of our sample stage with fluorescence detector and the X-ray optics that I showed earlier. And here we can stream the X-ray diffraction pattern as well as the X-ray fluorescence. It's bigger data set for sure. So here's a 20 millisecond image into that small diffraction detector and the integrated diffractogram from that. So if we make a map of that, here's a map from a thin section of an ear bone of a salmon. So you take a salmon and you cut out the ear bone, and when the salmon migrates, it goes from freshwater to saltwater, and it's thought that that will change what the metal uptake, and the ear bones are grow slowly but coherently and are actually well known and well loved for determining the age and provenance, or where the fish was. So in here, so this is the map of strontium and zinc, the X-ray fluorescent map, strontium and zinc in a slice through this bone that's in the fish's ear. You can see that the zinc, which is mostly with proteins that like attach the ear bone to the ear, are along this way, and you see these stripes in the strontium concentration as the amount of strontium in this calcium carbonate. It's a aragonite, so it's calcium carbonate. Strontium goes in. The amount of strontium changes with the seawater or the salinity, and so that tells you can basically age the fish that way. But then if you look at the diffraction pattern from that at different Q or D values, you see that the crystal structure is doing many weird and strange things, like where the diffraction patterns are striped, so that's giving you texture analysis, and there's variations on how much single crystal there is. So it's really an amazing set of data. This is also large, so this took an hour. It's 50 gigabytes, so it's not uncommon for people to need to like really manage the data size they have when they're doing diffraction, as well as fluorescence mapping. Okay, so another thing that we do hardly ever, so I'll talk about it, is XAFS at very high pressure in diamond anvil cells. So this is something so diamond anvil cell work is a very important part of GSECARS. We don't do much of it on the microprobe, but the nanocrystalline diamonds, especially from Tetsuo Irifune in Japan, are excellent for doing high pressure XAFS. I believe there was a talk on that in this series that talked about this. This is work from Xinghua Hong at Stony Brook University, looking at the topological insulators, bismuth selenide, and this shows really amazing phase changes with pressure. I won't go into the details, but we can do it's just to say that with these diamonds, the nanocrystalline diamonds, we can actually do really good extended XAFS with it. This was sort of a 10 micron beam, and over a few days, could measure both the silicon, the selenium, and the bismuth XAFS well enough to analyze the XAFS and understand the local structure. How am I doing on time? Okay, so but a really major part of our program is to look at microscale mineral phases and melt inclusions in volcanic minerals, glasses, with a main emphasis for deep earth and planetary sciences. So I think that some of this was discussed in earlier talks, especially from maybe Megan and from Darby Dyer. So a very important question for earth science is how much oxygen is actually available in the deep earth or on the moon or in other planets? How oxidized, how dry is the moon? And so XANES can be very useful for that, because over the log of FO2, so that's like pH, but for oxygen, how much oxygen is there? What's the partial pressure of oxygen? It ranges by something like 18 orders of magnitude over relevant conditions that we care about for planetary science, right? The Earth has no oxygen in the core and the surface is fully oxidized. So using all of the different metals, vanadium, iron, chromium, and europium as redox pairs, you can span the range of oxygen partial pressure. Each of these goes through a different sort of redox change at different levels of FO2. So we spend a lot of time, almost half the work we do is on the pre-H peaks or the XANES analysis of these elements in these ranges of oxidation state. So here are some of those typical spectra for iron, manganese. We do a little bit of manganese, but not too much. It's mostly iron, chromium, a lot of vanadium work. You can see vanadium has this huge pre-H peak like chromium, but it happens at all oxidation states that are available. So that's very easy to measure even when the vanadium concentration is 10 ppm and in a sample that's 10 microns in size. So you can isolate a melt inclusion, measure the vanadium oxidation state, and pull out the FO2. So that's really a major effort for us. Europium is also one of our favorite elements because it's redox sensitive. It's a rare earth element, and it has low at a relatively low FF2, and then titanium as well. So I think this is also a good place to pause. Oh, I should say, I have one slide here, one more slide. This is a good place to pause, but I'll put in the slide. We also are looking to do smaller and smaller samples. So here are titanium, vanadium, chromium on a sample that was extracted with a focused ion beam. It's 10 microns in size. We need to map this thing at micron scale. We want to go finer, and we're trying to get these really small features, really small items characterized. So it's a good place to pause for questions. Also, before I go on to some HERFD analysis, I'll bring this up and then we'll pause for questions.
All right. Jeremy, you had a question?
Hi, Matt. Just had a question. How do you get a diffraction ring from a microbeam? Since I saw nice rings in your diffraction pattern.
Right. Thanks, Jeremy. I totally skipped over that. Right. So we have a microbeam, and that was a really nanocrystalline sample. So that was one that was unusually good.
Okay.
When we do the microbeam work, right? So with a 2 micron beam and a 2 micron sample volume, or maybe 2 by 3, 2 by 5 micron sample volume, 2 by 2 by 5, nothing is a perfect crystal, and nothing is a perfect powder. Maybe you have a perfect crystal, but then actually you have a problem because we're not getting the whole ring. So we're not seeing the whole thing. So we can do phase ID because we know there's texture. We know we're not getting perfect rings. So we make a fluorescence map. We often will, integrate 10 pixels together that are nearby each other to get a better powder pattern. And we're hoping to get, we're planning, we're going to get a bigger detector, but we know that that's a problem. So
Okay.
We're not really analyzing those powder patterns for rebuild analysis because we don't have the intensity.
Yeah, I'm actually just surprised you get enough orientations enough to make an ID at an arbitrary energy or beam size.
It might be that I picked a really good one to show.
Okay.
And in that otolith, you can see that there's some real texture there, and as you scan that, some of those things really dance around quite a bit, and trying to figure out what that means for orientation, or are those single crystals that are rotating? Yeah, we need somebody to figure that out. And it's not me.
Okay, thanks.
Yeah.
Okay, Alessandra, you had a question about bromine?
Yeah, hi. Thank you for calling on me. I was wondering if that was very cool otolith data that you showed. And I was wondering if you had observed any elevated bromine in those otolith samples, because I recall having a really cool conversation with Karen Lindberg at SUNY ESF a couple of years ago. She works on otoliths. She's a biologist, and she found elevated bromine under hypoxic conditions deep in the seawater column. So I was wondering if you had noticed anything about bromine.
So I think we haven't seen anything with bromine in those otoliths. We have done some bromine work with other folks on marine samples. But I'm not sure I'm not sure I want to go into like the details of that science because I'll get it wrong. And so we have done some, and I think that we're always interested in doing stuff like that. So maybe that would be an interesting study to do.
Thank you.
Yeah.
Okay, Megan, you had a question?
Yeah, hi, Matt.
Hi, Megan. Did I say something wrong? Please correct
No,
me.
no, not at all. But I am disturbed by that basalt map you showed. That seemed to be highly crystalline. So I hope that's not I hope that's not LW0. But
that is not. No. That is not LW0. I can share offline with. No.
Okay.
No. That is not LW. That is no.
Matt, that's not one of my samples either. It's Darby. It just looks like a cryptocrystalline basalt. That didn't bother me at all.
Okay.
Yeah,
Great. I was just wondering if you had any like indication that the part of the crystallinity could be due to exposure to the high energy beam. So like we have this problem constantly with rhyolites that seem to have like evidence of microcrystalline magnetite that we can't really see in a petrographic scope, but is definitely there in the spectrum. So I don't know if these two things are analogous or this is something totally different.
I think that one map that I showed that looks really like an ugly glass, I think that's separate. That was a very dry sample, and I could, yeah, I know this is being recorded, so it was a very dry sample. I don't think that that's beam damage, and the presence of magnetite is interesting, but yeah, I would say talk to Darby about that.
Yeah, Megan, I will add that we see, like even in the samples we run on the Mossbauer that other people send us, I would say at least 50% of the time, if they say it's glass plus olivine or glass plus pyroxene. It's just that people don't look with very great care at what they are studying sometimes. And oftentimes it's below the resolution of the method that they're using to look at it.
Right.
Yeah, thank you.
Okay.
All right, Matt, you should continue.
Okay, so great, that was awesome. Right, so
without naming whoever sample of basalt that was. Yeah, just
whew, dodge that bullet. Okay, so one of the things that we're very interested in being able to do, and as everyone or many of the people who pay attention to this journal club know, is that high resolution XAFs, HERFD and RIXS are very important. We need to be able to do those. Not only because for high resolution XANES, although that's important, but actually one of the main features for us is to be able to do the backroom rejection and get the improved sensitivity at low concentrations. We have used in the past a wavelength dispersive spectrometer like you would attach to an SEM, but it's a real pain. So getting a dedicated system would really be useful, not only for just the high resolution XANES, but just as a wavelength dispersive spectrometer approach. So we really want this to be part of the microprobe. We can't really have dedicated like separate analyses because we need to be able to do the microprobe work for Megan and Darby and everybody else who comes. So the concept we have, and this is an early design concept, we have modified design concepts now, is to make a 1 meter roll-in circle system vertically deflecting and using commercial analyzers, the 4-inch analyzers, say from XRS Tech. We have some funding for this, actually, both NSF and DOE dedicated money. We ordered a dedicated area detector for that, and we're commissioning and building up analyzer sets for this, and we're collecting HERFD and some RIXS plane data. So far, our emphasis has been on copper, iron, and rare earth elements, which is actually what the DOE funding is for. So I'll show you some of that. Here's like some early commissioning work. So using a Pilatus detector and the sample in horizontal. So we took the fluorescence detector out. It's sitting over here. So we could do this, and we can measure HERFD copper. So here's copper from a 1 silicon 444 reflection, copper oxide. That worked well. And we've actually done with Tony and I have done some more real samples with copper. And it's quite interesting. We're interested, especially in the copper 1, this sharp resonance is there, and it would be nice to be able to figure out if that's, to be able to distinguish the ligand well. And we know that we could possibly do valence to core transitions, but the samples we're really interested in are at the 10 to 50 ppm range. So we're not sure that we can do valence to core, but we'll get there and try it. But we'd like to be able to do that with K-alpha HERFD. And then we can make some RIXS planes data. This was with Mauro Ravetzi, who came and visited last summer when he could, and helped us commission, like with this sort of setup, to be able to do RIXS planes data, so be able to do both emission and RIXS scans together. So this is that's one germanium 620 analyzer crystal and the iron and hematite. So that's interesting. You can see all the features that are known for the RIXS plane, that the pre-edge peaks are lined up and they don't show up so much in the low spin state, and so that's all there, and we're excited about being able to do that on a more regular basis. So more recently, so just a month ago, we've commissioned now, so we now have a system where we actually have 3 analyzers. These are 3 germanium 111 analyzers and our 7-element detector all in place. It's not, the alignment isn't perfect, but we're getting there. And so here our sample sits here, our 7-element detector sits here in our normal spot, and we can still see the HERFD signals and the analyzed signals from the going out to these 3 analyzers and to the same Eiger 500K detector. I think we can improve this helium environment. Maybe some of you have some ideas on how we might be able to do that. It looks great. So here's some early-ish europium L alpha. We're interested in doing europium and other rare earth elements. So here's an image on the Eiger 500 from the germanium 333 reflection. That's the europium L alpha. Actually, that's a zoomed in view of the full detector face with 75 micron pixels. That image is about 10 millimeters across. I think that's about the best focus we can do, and that's just the finite extent. The 4 inches of that analyzer don't make a circle from that sphere, and so that should be dispersed that way. I think we ought to be able to get a better focus in the vertical, but that might just be crystal quality. Anyway, we can make a small ROI in that region and integrate that to get out the signal for europium L alpha that's very highly, very low background. So here are 2 XANES spectra for europium 2+ and 3+. The peaks are beautifully separated. The energy resolution is quite good. This is from a powder sample, so actually there's probably some overabsorption in these spectra. If we do, then what we're really interested in is seeing how low in concentration we can go. So this is 5 ppm of europium in a glass, and it's a USGS glass, so we know it's got 5 ppm, and it has actually fairly low manganese, which would be the polluting element that really kills EDS analysis. But we think that that's not a problem at all. Here are the image of 3 analyzers on the same spot. So you can almost see that there's 3 overlapping there. And then that's the 5 ppm, about a half-hour scan. So it's totally reasonable to think that we can get to 1 ppm. We're not quite there yet, but we're going to get there. And I think at this point it's mostly that beautiful bag that we might be able to make a little less sterile, make it look a little less interesting and a little bit more industrial. So then those are the 3 peaks, and the spots are 3 by 10 millimeters, again, showing out of circle alignment. And the co-alignment, so this is well known for, I'm sure all of you doing HERFD or emission spectra know this, but if I can tweak each of those crystals individually, and if I move these 3 overlapping stripes so that they're displaced by even a few millimeters, the peak energy that they see has changed enough to kill the resolution. So it's important to be able to do these, to be able to do some of the setup for scanning these and get those to be aligned. And we're still sort of learning how to do that efficiently so that we can switch analyzers. But I should say that in the November run, we did switch analyzer crystals and which element we were looking at. It took an hour or so. So it's not crazy to think about doing different analyzed lines in a single user run, but we'll probably want to do 1 or 2 at a time. That's just for those users who might be thinking, "Ooh, I can do zinc, copper, and vanadium all in the same run." Maybe not. Okay, so I'm gonna conclude early because I think that there's a lot that we could discuss. But the APS upgrade is coming soon, mid 2022, which is, we've been in COVID isolation for 8 months, and this is 18 months away. So it's really getting close. By the time we get back to the lab full time, we won't have much time to get ready for this. So the APS upgrade will make the beam more or less circular instead of a line, that the X-ray beam coming out of the undulator. And we believe that we will routinely be working at a half a micron beam size instead of routinely working at 1 to 2. And we will not need, we think, as Cheng Young asked, we don't think we'll need the secondary source. We'll still have it in place. We won't remove it so that because some of the modes still have the horizontal beam size twice as big as the vertical. We think that with that, the flux should increase by a factor of 10 or so. We need improved mirrors to be able to get to the half micron size, but the APS beamline enhancement process has promised us that. We'll see how that happens. They also need to replace our undulator. One of the things, so when we upgraded our beamline in 2012, they said, yes, we will pay for your undulator. And then we said, great, can we have a new one? And I think they felt like they got taken. And so now maybe in retaliation, we're going to get an APS undulator A, a 33 millimeter device, one that already exists. But we also asked for something else from them. We're trying to work with them. We'll keep the magnets from an undulator A, but we want the mechanism, the actual movement of the undulator, of the frame to be improved. And we're working with them on that. We hope to be able to do better coordinated energy scanning so that we can do XANES measurements in faster than a half a second per point. One of the things that we know we need to get to half a micron stability is actually stability of the sample and beam together. We know the X-ray beam at the APS moves a bit. We can measure that. We have lots of measurements on that. I could talk about that for another hour. But also our sample stack moves a bit too. So we know we need to work on that. And so we've already replaced the table we had with a granite block that's tied well to the floor and has greatly improved our stability of our sample. And now we're just waiting for the X-ray optics to get small enough so that we can push against really what we know is a really, really small beam. Half a micron is actually really small. So I think with that, I'll take any questions or any discussion, and here's some links if you're interested. So for those of you who haven't used or aren't familiar, our Beamline is open for outside users. We do a lot of outside user work. We're always looking for new and interesting users, especially in Earth-ish science work. So you can go to this website for the GSECARS, and if you're interested in X-ray absorption at all, you should visit the X-ray Absorption Society website that I'm partially involved with, at least on occasion. So with that, I'll ask for any other questions.
Thank you, Matt. Great talk. We'll start off with a question from Matthew Marcus.
Great.
Yes. Well, two questions I had. One is about I noticed that your I0 monitor was before the mirrors, the KB mirrors, and I was wondering if that caused a problem because the transmission of the KB mirrors depends so critically on the beam position and also on any stray light that that happens to be incident.
Yeah, right. So that's right. We do have the ability to put an ion chamber downstream, and we hardly ever do that. But you're right. Actually, so for us, I'll just go, so for you, Matthew, for us, okay, so we have those beamline mirrors are at 3 milliradians. And so those do harmonic rejection. For silicon, that does harmonic rejection above 10.5 keV, or it passes 10.5 keV-ish. Let's just say 10.5. So if we're at sulfur, we're getting the third harmonic over those from those 3 milliradian mirrors. We can't avoid it. We're getting 2.5 and 7.5 keV X-rays from those mirrors. So in I0, there's a lot of harmonics. We can put the small KB mirrors downstream at higher pitch. We do that. We can put those at 5 or 6 milliradians to reject the harmonics hitting the beam, but the harmonics hitting I0, we can't always avoid. In addition, like you say, if there's any imperfections in those mirrors reflecting, or even with harmonic rejection ignored, and so we have slits in front of the mirrors, and we restrict that aperture pretty well. So the drifts and the normalizations are not disastrous, but I would also say that for us, getting really good extended XAFs on a tiny spot is challenging. We can get decent XAFs on 10 microns objects, and below that it's not perfect. And for sulfur, I would say that we do XANES, and maybe even chlorine. I would say we do XANES, and we can't quite do XAFs because of the harmonic projection. Yeah.
Yeah, and also with the secondary, let's see, with the APSU, you were talking about removing the secondary source, and I wonder if the incident beam will be stable enough to let you get away with that.
Yeah, we're unsure. We actually do feedback. We have it was in there, but I didn't talk about it. We have a foil BPM. It's like 4 diodes looking at a foil. The beam goes through the foil, and we look at the fluorescence off of those to stable. Then we can stabilize the position. In fact, above about 4 keV, we don't do any feedback on that, but we monitor that, and we'll have little scripts that run to keep the beam position pointing in the same position at 40 meters from the source. So that level of stability we take care of. We actually, so Peter Eng and myself, we sort of obsess about checking for the beam motion upstream, and we check that the beam hitting our monochromator is stable, and we'll ask the APS for steering whenever we want, and we'll do that regularly, usually a couple of times around. And the APSU, we just don't know what that's going to be. So keeping that source available is good. I should also say, like, because you asked, I'll just toss out this question. We slit the front end at the front end and in the SSA, and so the object we're actually imaging with our small KB mirrors is an image that has Fresnel fringes in it. We cannot take the full source for heat load reasons, and I don't even know if we can take the full source for like size reasons everywhere for like illuminating our mirror. So we're not really focusing a Gaussian source. We're focusing a source with clear fringes, and the coherence will get worse, or no, it'll get better. No, I don't know which it is. It'll get more coherent with the APSU. We're scared by that.
Okay, thanks.
Yeah.
All right. Renee Bess and I had a really similar question, so I'll go ahead and ask it. If you can go back to that image with the 3 overlaying reflections, yeah, that. Why did you choose to have them overlapping? Because
yeah, so my view is, so I'd like to hear your point out. So our spot size, the source for this is really small. It's, microns. I think that unless I have those at the same position on the detector, I don't have the same roll-in circles. And in fact, if I move one of, there's tilts, right? So there's tilt motors, and if I move one up, just like up here, and then I do the emission scan, it will peak at a different energy.
Yes.
And so I want them to be the same energy. I guess I could do like separate ROIs for those, and then get different. It'd be analyzing different energies.
Tweak the Bragg angle on the analyzers independently. Yeah, the worry here is exactly that you don't. To me, this makes it harder to check by doing like an elastic line scan, that they're all 3 at exactly the same energy. And so my intuition would have been to put them on separate spots.
So actually what I did was I put them, each of them I can put to this spot. I don't have it here, but I make a rectangular ROI. That's also like something worth discussing. Do I want a smarter ROI? I make a rectangular ROI. I can put each one in, and then out of that ROI, and then do the emissions, emission scan to see that they're all sort of lined up pretty well. And within, for europium L alpha on germanium 111.
That's a pretty wide line. Yeah.
Yeah, it's pretty wide, but they were very close. So I haven't tried that yet on other lines, but yes, I'm slightly concerned about that. But
yeah, my intuition would have been to intentionally cant the 3 roll-in circles so that you knew they'd go to different places. and then use the elastic line to get them nailed to the same energy.
Yeah, but then there'll be a dispersion. I'll be measuring, right? Then I have to do an energy shift of the emission lines or of the ZANES. The ZANES will be
not
shifted.
obvious. I mean, you just shim the circles so that they're not all coming to the same point. You won't get as sharp a focus because you have a planar detector, but that's not going to matter much.
Sure. Yeah. I can definitely tweak these away so that they're still on the detector and measure them separately. But then the ZANE scan across that, those ZANE scans from each of those will be shifted in energy, right?
I don't see that. They're 3 independent Rowland circles. You can tune each one to whatever energy you want. You've just you're just rotating the plane of the 2 outer Rowland circles with respect to the one in the middle.
Right. Okay. Right. Yeah. What I've done here is to try to get them to be 3 Rowland circles of the same size. Right.
At the same place.
Yeah.
Right.
With this, I guess. Right. So that there's with the same. Well, I mean, that have 2 points together, right? So then they're just circles that.
Yeah. I understand. Like lyrics. Yeah.
Yeah. Right. So that's an interest. So we'll have to play with that.
Yeah.
That's a good thing.
We're out of time, but I want to talk about helium. No, we're not out of time. There's one last thing I really want you to address. What are the lessons learned about operating a beamline during COVID that you think will carry over into operations post-COVID? You're the right guy to ask this to.
Yeah. So we've been doing remote work since June or July-ish, and people are mailing in samples. And so I didn't talk about software at all. So our data collection system is pretty fluid for users to be able to use. We have users today, right now, logged in from New York and collecting data in our beamline using, a virtual connection to our beamline computer and mailing in samples. So we have a decent system for setting up macros that can be programmatically programmed so that the users can see an optical image of their sample, make an X-ray fluorescence map, use the X-ray fluorescence map to define where they want to do the ZANES, and then script all of that. So I think we actually expect that we're going to be doing remote users for a good portion of our users going forward, that we've learned how to do this and we're not going back at least all the way. For sure, there are some users, hi Darby, who need to have people come on site and do the hard stuff. But there are also some users, maybe even Megan or Mary Jo, who can mail in samples, and then Tony and I load them up, and they can run the beamline, and they have their, actually the stuff we do where people bring thin sections and map them and do the ZANES, they can go for days without changing samples. So we think that that's going to be sort of normal for us. We're also because with all the detector changes and all this stuff, we're also pushing as much as we can to go faster, just so we get bigger maps, more ZANES spectra per product.
Great. Yeah. I mean, I think another thing that may come out of having so much mail-in capability is sort of a higher equity of access. People at smaller schools who don't have a lot of travel budget now can get access if they get the GP system.
That is completely correct. Actually, for us, it's also not just, it's also some foreign access. It's really a lot of work for people to come from Australia, but mailing the samples from Australia is less work.
Yeah, I also have some Australian users, and they've been able to run, and it saves them a ton of money. And in general, it also helps with scheduling because people don't have to schedule travel.
Right.
So they can, so that they can do it while they're also doing their other duties.
Exactly. Yeah. Yeah. So yeah, like Jerry says, for the smaller institutions or for the professors at colleges, right, who aren't it just seems like that's a very convenient thing to be able to do.
Yeah, even big institutions, travel is a major cost.
Absolutely. Yeah. And yeah, right. I think it also like though, there's an interesting thing. So Matthew and Jerry, it also sort of blows up the idea that you need a regional facility, that, you know, the beamline in your backyard is the one you go to. So I think that might actually be an important like change that happens over the next 5 years, is that this idea that you need a regional source that you can drive to. No, you can mail the samples easy. You can drive to the.
I think that'll still be around for those cases where you really do need the hands-on, like the in situ, the setups, and so forth.
Oh, for sure. And I would say that there are lots of methods where mail-in just is a lot harder to imagine. But for us, for this microprobe, and maybe for a lot of XAFS beamlines too, you know, once it's in place, it's, you know, like I said, we're probably going to be at 50% mail-in for the foreseeable future.